So to close off today's discussion, I'm going to present a type of random variable that's very important to us. We're dealing with an awful lot. And that is the Gaussian random variable. So this is a continuous value random variable. You may have heard of this under different names. It's sometimes called the standard normal or the normal, or less formally it's sometimes called the bell curve. So if x is Gaussian distributed with mean, they use a different symbol usually. They use mu for the mean. So the mean is mu, and the variance is sigma squared. Then the probability density function, let me write that, mean, variance. The probability density function of x is 1 over root 2 pi variance. I'm going to write exp, which stands for e to the power of, just because it's tough to write e to the power of a big complicated expression, minus 1 over 2 sigma squared times 2 times variance times x minus mean squared, like that. So once again, exp, that just means e to the power of all this. And if you plot that out, you get the familiar bell curve centered at mu. Okay, some important things to remember about the Gaussian is that once you know, in order to characterize the Gaussian, you need to know the mean and the variance. So these will be given to you. And once you know mean and variance, then you can just write this, and the Gaussian random variable is dependent only on that, only on mean and variance. So a nice property of Gaussian random variables is that if x is Gaussian and y is Gaussian, let's call it with mean mu x and variance sigma squared x, y is Gaussian with mean mu y and variance sigma squared y, then x plus y, let's call that z, is also Gaussian with mean mu z. What do you think mu z is? So expected value of z is the expected value of x plus y. What can I do with that?
Expected value of x plus expected value.
Correct, which is mean x plus mean y. The variance of z I will leave this as a homework assignment. I'll put this on the problem set, on the next problem set. But the variance of z is the variance of x plus the variance of y. But this is only true if x and y are independent. It's not too hard to show that, and I'll put it in the problem set. Okay, so if I ask you some other properties of the Gaussian. Actually, let me say this. If I ask you what's the probability, if x is Gaussian, what's the probability that x is 0 for something, if the mean is non-zero? This is equal to the integral from 0 to infinity of f of x. But if I substitute this in, that integral can't be calculated in closed form because it has an e to the x squared, so there's no closed form way to do that. There are ways around that. There are tables of integrals. So what you could do is you can look it up in a table. There is a special function that actually corresponds to the integral of this function that we're going to deal with somewhat. We'll talk about it later. It's called curve C. It's a special name function. That stands for error function complementary. So basically, the idea is you take your Gaussian integral, transform, use lots of changes of variables until you get it into the right form for curve C, and then look it up in the table, in a table of values for curve C. Or there's a MATLAB function called curve C that you can also use. But there are some shortcuts. So for one thing, f of x is even about u. By even, I mean symmetric. So in other words, the integral from mu plus some constant k to infinity of f of x dx is equal to the integral from minus infinity to mu minus k f x dx. And that's pretty easy to see. So if we're centered around mu, and I take the weight of this function k to infinity, because it's symmetric about u, about mu, from minus k to minus infinity will have the same area. So in other words, if you set up your integral once and look it up in the table for this, and now you need that, you don't need to look it up in the table again because you use the same values, they're equal. Another thing is integral from mu to infinity of f of x is 1/2. So if you start at the mean, the total area of the rest of the curve is 1/2. What do you think it is for integral minus infinity to u? So this property, it's again 1/2. Okay, I think that's just about all the properties we're going to need of the Gaussian. Any questions on that? So this was a fairly quick review today, and we went quite fast, but that's basically all of the probability stuff that we're going to need. So there's hopefully you remember all of this. Hopefully it's all starting to come back to you because we will be using pretty much all of these concepts through the rest of the course. Any questions? Okay, once again, there's no lab on Friday. Lab starts next week, and we'll see you on Tuesday.
Good morning.